Hello friends, welcome to the Distributed PostgreSQL Essentials course. In this course you will learn how to build scalable and fault-tolerant applications that run on a distributed version of Postgres. Throughout the course you're going to build a generative AI application. The application is going to take user questions in plain English and then provide the users with various movie recommendations. The structure of the course looks as follows. First, we will deploy the initial version of the application on a single server Postgres instance. Then we will learn how to transition this application to a multi-node distributed PostgreSQL cluster. And by doing that, we will learn how to achieve horizontal scalability with our distributed Postgres instance. Then we will discuss how to achieve high availability across zones, data centers, and regions. Then we will practice deploying and configuring a geo-partitioned distributed PostgreSQL cluster so that we can achieve low latency reads and writes for all of the users across all of the distant locations. In the end, I'd like to show you how you can deploy Postgres as a fully managed service in the cloud with the configuration that you need. So if the structure of the course sounds appealing to you, then let's do a deep dive. Alright, welcome to the first chapter of the course, my friend. In this chapter, you learn how to deploy the movie recommendation service over a single server Postgres instance. Just in case, the name of the service is YugabyteDB. So that, as I already mentioned, what the service does, it takes user questions in plain English and then uses an OpenAI embedding model and the PostgreSQL pgvector extension to search through the data that is stored in your database and then to provide you with various movie recommendations. If you decide to follow this course on your end, then you need to remember three things. First, you need to install Docker because the database and the application are going to be deployed as containers. Second, the application uses an OpenAI embedding model, which requires you to provide an OpenAI API key. So if you don't have that API key yet, then go to the platform openai.com and create an account there. And lastly, in the end, I will provide you with a link to a complete step-by-step tutorial that you will be able to follow on your end. Sounds like a good plan? Then let's go. Let's begin with PostgreSQL deployment on our own laptops. I will be using the latest version of Postgres with the pgvector extension pre-installed. We are going to deploy the database in Docker. First, I will create a special network where I will deploy my database. The name of the network is going to be Yuga plus network. Then I want to create a special directory that will be used as a volume for my PostgreSQL container. The name is going to be Postgres volume. Lastly, this is how the docker run command looks like. The name of the container is going to be Postgres. The container is going to be deployed on our just created Yuga Plus network. This is the name of the user and the password. Certainly don't use this combination in production. That's the port number that the database is going to listen on, and we are exposing this port number to our host operating system so that I can connect from my tools and application from the host if necessary. That's our volume, and the Postgres related data of the container is going to be stored in this volume. And lastly, this is the name of the image that I'm using. This image comes with the pgvector extension prepackaged, and as I said, the pgvector is required for the application because it enables the vector similarity search over the database. Let's start it. And next, why don't we go ahead and connect to the database using PSQ2, and I connect to the container from the host. Okay, we are in. And right now we don't have any relations because we have to start our application first. Also, even though the pgvector extension comes prepackaged with Postgres, we need to explicitly enable it. You need to execute create extension command and pass the name of the extension, which is vector. Now the extension is created, the database is running, and we are ready to start our application. Jumping back to the application GitHub, I want to copy the URL. If I go to the downloads folder on my machine, And I will use git clone command to clone their application there. It's ready. And finally, let me open this application in Visual Studio Code. Next, how about doing a quick tour of the application structure, my friend? The application comes with two main components, the backend and the frontend. The backend is written in Java. It uses the Spring AI framework, and the frontend is written in JavaScript and uses the React framework. Once the backend starts, it will enable the following database migration files. It uses the Flyway framework for that. For instance, the first file creates the vector, PG vector extension. Then it will create the movie table, and this movie table stores information about various movies with overviews, genres, titles, etc. Once the table is created, the application will preload this sample dataset. And this sample dataset already comes with embeddings, the vectorized representation of the movie overviews. After that, it will create the user account table, and it will populate the table with several dummy users. In the end, we will create the user library table. The user library table stores user-specific information about the movies that user wants to watch or already watching. I do understand that not everyone uses Java. That's why I don't want us to look into the implementation details of the backend, because you might be using JavaScript, Python, Go, Rust, and that's why today we are going to use Docker for the application deployment. We have this Docker compose file. It will start an instance of backend, and the backend will connect to the same Yuga Plus network where we have our database running. Once started, the backend will connect to the PostgreSQL container, and that's the name of our Postgres container. That's the name, the user, and the password. We are using the Postgres JDBC driver. And finally, we need to provide our OpenAI developer key. The frontend also will be started on the same network. Once the backend is up and running, the frontend will be able to run as well. And the frontend will redirect all the traffic, all the requests to the following backend endpoint. Sounds nice? Sounds cool? Let me provide my OpenAI key in the following configuration, and then I will start it. So this is how my OpenAI API key looks like. Now everything is ready. Let's go to terminal and start our application. I'm using Docker compose app command, and I'm telling to build the images. It will take some time to build the backend and the frontend, but I think that within a minute we'll get this application running on our laptops. So let's wait a little bit. Finally, the backend has successfully started, and right now it applies the schema migrations. According to the logs, the database was created successfully. And I think that the front end, is already up and running as well. And we can connect to it by going to this address. Let me copy it and jump to my browser. All right, welcome to the application. And we will sign in with this default user. So this is how the application interface looks like. Now, let's say I want to search for some movie recommendations. For instance, I'd like to watch a movie about space adventures. We are doing the search, and then what happens? The application connects to the backend. It takes this user prompt, it connects to the OpenAI, it uses the OpenAI embedding model to generate a vectorized representation for this prompt. Then it performs the vector similarity search over the data that is stored in my Postgres database, and these movies are retrieved from Postgres. So this is how it works in practice. Also, you can pre-filter the data before performing this vector similarity search. You can be more specific. For instance, you can say that you are interested only in the movies with rank 7 or above, and the category of the movies is science fiction. If you do the search, this is what's going to be recommended: Interstellar, Gravity, and Arrival. With that, congratulations, we have successfully completed chapter number 1 of this course. we learned how to deploy this movie recommendation service in Docker and get it working with a single server Postgres instance. And now let's move forward to the chapter number 2, where we will learn how to deploy the same application over a multi-node distributed PostgreSQL cluster. Alright, my friend, as long as the goal of chapter number 2 of this course is to transition this application to a multi-node distributed PostgreSQL cluster, we need to figure out what do we understand under the distributed PostgreSQL. Because those of you who are familiar with Postgres, that the database is not designed by default for distributed deployments. Usually you take Postgres and deploy it in a single server configuration. This is what we exactly did in chapter number 1. However, the ecosystem of Postgres is so rich that you will find several options for making your Postgres horizontally scalable and distributed. Then an obvious question to us is, what version of the distributed PostgreSQL are we going to use in this course? How about we ask Google, the distributed Postgres guide. And clicking this link. I authored this guide in the end of the previous year. And as I said, depending on the person you are talking to, different folks can mean different configuration under the name of distributed PostgreSQL. And this article, I am discussing 3 possible options. Some folks say that a distributed PostgreSQL is a Postgres that is configured in a multi-master configuration with asynchronous or synchronous replication. And here is a sample configuration with the Postgres running across 3 availability zones. We have one primary instance in zone A and then primary instances in zone B and zone C of some cloud environment. Then the application can connect to any of these instances and execute read and write requests. And this configuration allows you to scale reads and writes. And then the replication is set between those primary instances to make sure that the changes are replicated. Also, the standbys are necessary for every primary to make sure that this configuration is fault tolerant and can tolerate different outages. Next, the second configuration is multi-master sharded PostgreSQL with coordinator. And here is we are talking about the sharding solutions such as Citus Data, Microsoft Cosmos DB, or Amazon Aurora Limitless. Basic configuration can look as follows. You take your tables and you shard those tables, and then you distribute those shards across different instances of Postgres, and the data is mapped to those shards. This is how you can achieve horizontal scalability. However, then the application needs to connect to a coordinator node, and the coordinator decides on the execution of requests. It's aware about the data distribution. And also don't forget that you need to add standby instances to all of those nodes that store your shards. The last configuration is multi-master shared nothing PostgreSQL. In the previous example, we used coordinator, and this is your single point of failure, and this might become your bottleneck. But in a shared nothing architecture, we don't have any single point that makes all of those decisions. And in the Postgres ecosystem, we have YugabyteDB, and YugabyteDB is a distributed SQL database that is built on Postgres. It's literally a distributed PostgreSQL cluster. From the configuration standpoint, you just span a multi-node YugabyteDB cluster across several zones, regions, or data centers, and the application just connects to those nodes and executes the request. I will be using this configuration, which means that in our case, distributed PostgreSQL will be YugabyteDB. If you are interested in exploring the other configurations, then just watch this video that I recorded and published earlier, and you will find the link to this video in the description to this course. In the meantime, let's go ahead and deploy our first multi-node YugabyteDB cluster on our own laptops. Similar to Postgres, YugabyteDB is open source. It's available under the Apache 2.0 license, which means that you can take it and deploy it whenever you like. Let it be your own laptop, your private data center, or your preferred cloud environment. I will be deploying YugabyteDB in Docker. First, I need to create a directory that will be used as a volume for my YugabyteDB containers. The name will be Yugabyte volume. Next, I'm using the following docker run command that will start the first node of YugabyteDB on my machine. That node will be running on the Yuga Plus network, the same network that we are using for the application containers. Then we will expose the following ports to the host operating system. This port number is the port of the UI, where you can take a look at some of the cluster statistics. And this is the port where the database listens to application connections. Next, this is the directory that is used as a volume, and the first node is going to use this node1 subdirectory for the YugabyteDB specific data. Once the container is started, I will use the YugabyteDB tool that helps us to start the cluster easily. I will start the node and I'm telling that's the base directory, and this base directory is mapped to the volume of node number 1. It's quite simple. Let's go ahead and deploy it. Once it's started, we can connect to the cluster from our local host using the same PostgreSQL tool. The IP address is the same, but the port number is different this time. YugabyteDB listens on port 5433, and the username by default is Yugabyte. So we connected to YugabyteDB using the same tools of Postgres, and we don't have any relations yet. At the same time, we have a special function from YugabyteDB servers that returns us all the servers, all the nodes that are presently available in the cluster. So let me do it this way. X on. Yeah, that's the node that we have running. Also remember that we can connect to the UI that provides us with some information about the state of the cluster. Jumping back to my browser, and here is localhost 1433. We have information about the total number of nodes that are running. We have just one node in our cluster. Right now, this configuration is not that much different from the configuration that we have with a single server Postgres cluster. That's why we need to be able to scale horizontally. Next, I want to increase the cluster size to 3 nodes from 1 to 3. How do we do this with YugabyteDB? It's easy, my friend. Jumping back to the terminal, let me split it. I'm using the same docker run command to start the second node. The name of this node is going to be YugabyteDB node 2. Then we have the same configuration like Yuga plus network, the port numbers, and then that's the volume, but the data of this node is going to be located under node 2 subdirectory of our volume. And then we are using the same YugabyteDB tool to start this node, and we are asking this node to join this container, YugabyteDB node number 1. Okay, let's start it. And then I want to repeat the same, but for node number 3. And that third node also connects to the node number 1. This is how it joins the cluster. All right, looks good. Now let's jump back to our PostgreSQL connection and see how many servers do we have right now in our cluster. Now we have 3 nodes in our cluster. That's the first node, the second one, and the third one. Excellent. If we go back to the UI and refresh the screen, you can find the same information. We have 3 nodes. All the nodes are healthy. They are running on our own laptop. YugabyteDB is a distributed database, which means it will take your tables, split them into shards, and distribute those shards across the entire cluster. YugabyteDB uses the term of tablets to define shards. So tablets are shards in YugabyteDB. Also, it's a transactional database. It uses the Raft consensus protocol to replicate the changes across the nodes. Presently, we don't have any application tables in the cluster, but there are some system level tables. Every node stores 9 tablets, 9 shards. And as long as YugabyteDB uses Raft consensus protocol, there is always a shard leader. So it's said that node number 1 is the leader for 3 shards. And the other nodes are leaders for the remaining shards of the cluster. Also, in Raft, we have the definition of followers or peers, which means that for every shard leader, we need to have at least 2 followers. And how does YugabyteDB decide on how many followers do we need? It depends on the replication factor, and presently the replication factor is set to 3, which means that for every shard, there are going to be 3 copies of the data. There will be the primary copy of the data that is stored on the leader, and the leader will be processing the read and write request by default for the data that is stored in that shard. And also there will be 2 copies of the data that is stored on followers or peers. So this is the configuration. And by distributing the data this way and by using this Raft consensus protocol, you will be able to execute your distributed transactions and requests in parallel over your cluster. And every cluster node will be able to handle the read and write requests for the data it's primary for. Okay, makes sense. Now, how about we go ahead and switch our application to this distributed YugabyteDB cluster? All we need to do is to jump back to our application and go to the Docker compose YAML file. What we need to change? We need to change the database URL. We still are going to use JDBC driver. We are going to use the PostgreSQL JDBC driver. However, right now we are connecting to the cluster. How about we connect to the cluster using YugabyteDB node 1? Then, if you remember, the nodes of YugabyteDB listen on port number 5433. And yeah, we will connect to the database Yugabyte. So that's the only change. We will continue using the PostgreSQL driver. Why? Because YugabyteDB is built on Postgres. It's literally distributed Postgres, which means that you can reuse libraries, drivers, and frameworks that you created for the standard Postgres deployments. The username is Yugabyte and the password is Yugabyte as well. Make sure you change this combination whenever you go in production. Yeah, and that's our driver and that's our OpenAI API key. That's it. That's all I need to do. I'm not going to change my application. I'm not going to change the definition of my schemas. YugabyteDB is feature and runtime compatible with Postgres. So the transitioning is very straightforward. Now, let's make sure that this change works. I'm stopping my container. Stopped. And the next Docker compose up. We don't need to rebuild anything. We're just restoring the containers. Spring started, it connected to YugabyteDB. Now the database has been applying the database migrations. So we created the movie table. Wonderful. Their application is up and running and it's ready. First, let me jump back to YugabyteDB UI. I'm going to the databases and you can see that we created those tables. That's the system table that is used by Flyway. That's the tool that applies those database migrations. Excellent. What if we go to the application UI? It's refreshed because right now the UI is connected to the new backend instance and we need to sign in one more time. Okay, and what do we like to watch? I'd like to watch a movie about a space adventure with an unexpected ending. Yeah, we are getting these results. Let's be more specific. We are pre-filtering the data before performing the vector similarity search, and we are getting the following recommendation: Interstellar, Gravity, and Star Trek. And similarly to Postgres, YugabyteDB uses the PG vector extension to perform this vector similarity search. Wonderful. And with that, congratulations, my friend. We successfully completed chapter number 2 of the course. Learned how to deploy a multi-node distributed PostgreSQL cluster, and then how to transition this generative AI application to the cluster with no code level changes. Next, let's move forward with the chapter number 3, where you will learn how to tolerate outages even in the event of major incidents in the cloud. Alright, my friends, in chapter number 3, you will understand that in addition to the scalability, high availability is another big reason why many select distributed PostgreSQL deployments. Let's perform the following experiment. What we already have. We have a 3-node YugabyteDB cluster running. And if you jump back to the cluster UI, you will see that right now all of the nodes are running and they are healthy. Also, our replication factor is set to 3, meaning that every node in the cluster keeps a copy of your data. There are 3 copies of the data in the database stored for every record. And now what I want to show you, I want to emulate an outage. How about we go ahead and stop the first node and see what's gonna happen. However, first, let's do the following. I will connect to this node and I want to see how many movies do I have in the database. Right now we have 2,835 movies. Next, let me go to the Docker desktop UI and I will find this node number 1. I want to stop it. The node is stopped. If I jump back to the terminal, and try to execute this request. Yeah, it said that the terminal connection has failed. It's expected. If I go to their database UI and refresh the screen, nothing will happen because this UI was running on the first node that we have just stopped. At the same time, we have two other nodes in the database, and those two nodes are healthy. They still form a raft group, and I can connect to these nodes and execute my requests. Also, a quick test, the application was also by default connected to the first node. If I try to run this prompt one more time, yeah, I will not get anything. I think that I'm getting an exception. Yep, it's failed to obtain a JDBC connection. If we go to the Visual Studio Code and scroll up a little bit, yeah, just failing. We cannot connect to the cluster. And that happens because the application was connected to the first node. Now, let's try to connect to the second node and confirm that we are still up and running. What can we do? So here is the port numbers that are exposed for the second node. For instance, I can use port 5434 to connect to this node from my host operating system. Let's open this connection. I'm just changing the port number. And I'm in. All the data is here. How about we check the number of movies? All the movies are there. There is no any data loss, even though one of my database nodes is down. Also, I can go to the UI of this node. The port number is 15434. Let's go here and change it. 5434. Excellent. The cluster is live and healthy. These two nodes are running and they're capable of processing our requests, and the first node is down. So let's quickly summarize what you have just seen. We simulated an outage. In real life, it can be server level outage, data center outage, zone level outage, or even region level outage. But even though one of those nodes went down, our distributed database cluster remained operational. However, the application has failed. Why? Because it was not connected to the nodes that stayed alive. We can easily address this. All we need to do is to use another driver. Overall, when we are talking about the PostgreSQL JDBC driver, it's also possible to provide several connection endpoints. We could have listed all of those nodes in the connection URL here, and that would work for our use case that we have just emulated. However, in real production environments, you can add new nodes, you can delete nodes, you can scale it out, you can scale it down, whatever you want, which means that the list of the nodes the application needs to be aware of is not fixed, it's not static. That's why what I want to do next, I want us to use the smart driver of YugabyteDB. And the beauty of that driver is that it's aware of the cluster deployment. The driver can connect to any of the nodes, and then the driver will learn IP addresses of other nodes that are running in your database. And that will allow you to withstand all sorts of possible outages. Where can you find details about the smart driver? It's easy. I usually go to the YugabyteDB technical documentation. You can type in smart driver. I'm using Java. So generally what you need to do, you need to provide this dependency, and then you need to update your connection string. Also, once the driver is aware of your cluster topology, it will be able to load balance your requests. It will be able to send your application requests to all of the nodes, and that will help you to distribute the load across the entire cluster. Okay, so let's switch this driver and then simulate the outage one more time and see how the application responds to that outage. I need to go to my Palm XML file in the backend first. How to enable the smart driver. So the driver is enabled. Yes, I want to reload my dependencies. And next, what I need to do here in the database URL, the name of our driver is going to be YugabyteDB. We are still going to connect to the YugabyteDB node number 1. We will bring it back to the cluster. Not a big deal. And this part does not change. Also, I want the driver to load balance requests across the cluster. That's why I'm setting this load balance true parameter. And the driver class name that we need to pass, it's no longer the PostgreSQL JDBC driver, that's the YugabyteDB driver. That's it. That's all we need to do. Let me jump back to the terminal. And now I want to bring the first node back to the cluster. First, I want to remove the first node's container. And I will explain you why. I did that because I want to adjust the command that I used to start the first node in the container. As long as I already have two nodes running in my cluster, I want the first node to join the cluster because it's no longer the first node. I will ask it to join the YugabyteDB node number 2. Okay, so the container has been started. If you go to the Docker desktop UI, you will see that the node is up and running. Wonderful. How about we jump back to the UI that is running on our second node and refresh the screen. Excellent, the first node successfully joined back the cluster. And this means that we are ready for our final step. We need to bring back our application, and the application will be using the smart driver this time to connect to the database. The instance is stopped, and now I just need to do the Docker Compose app. Cool, the application is back, and it's successfully connected to the cluster using our smart driver. Let's go to the application. Yeah, we need to sign back. And what are the funniest comedy movies worth watching? Excellent, we've got a list of recommendations. Now we are ready to repeat our experiment by typing the same node number 1 and checking how the application will respond. Jumping back to my terminal, and let's do docker stop YugabyteDB node number 1. The node is down. And we can easily check that by going to the user interface. You can see that, yeah, the first node is down. Now I'm going back to my application, and how about I ask this, what are the scariest movies worth watching? Let's do the search. This time we've got this response. The application is up and running, and it retrieves all this data and performs the vector similarity search of the other two nodes that are still in their cluster. If we go to the Visual Studio Code, we don't see any exceptions here, which means that even though the smart driver was first connected to the node number 1, which is down right now, the application remained operational. So this is how you can tolerate various outages with YugabyteDB, whether we are talking about server level outages, zone level outages, data center outages, or even region level outages. Congratulations, my friend, we have successfully completed chapter number 3 of the course. And let's move forward to chapter number 4, where you will learn how to build global applications that rely on a distributed PostgreSQL deployments spanning several data centers, cloud regions, or other distant locations. Alright, let's dive into chapter number 4 of the course, my friend. Before we start, I want to show you an exceptional resource that is available on the YugabyteDB technical documentation. I go to the develop section, and here you will find the section that is dedicated to the global applications. And the first question, why would you want to build global applications that span data centers, regions, and other distant locations? One of the reasons we have already explored. It's all related to high availability. If you want to tolerate zone, region, or data center level outages, you want your application and you want your database to span distant locations. Another reason is data regulatory requirements. If you need your user data to be stored in specific data centers and cloud locations, that's another reason for building global applications. And the last reason for building global applications is low latency. Yes, it might sound counterintuitive for many of you, because we know if you deploy something across multiple regions, then you expect to get a performance hit. But in real life, if you deploy your database across multiple regions properly and bring the application data close enough to the users, then you will be able to serve user requests with lowest latency regardless of the user location. Okay, so that's another reason for building global applications, low latency. However, it's also worth noting that when it comes to global application design patterns, there is no any silver bullet solution. you would need to decide. On this page, you have 8 design patterns that will help you to find the right balance between low latency, between high availability, and especially if you want to comply with data regulatory requirements. Today, we are going to take a look at 2 design patterns from this list. We will deploy a multi-region database instance on our local laptops. We will start with this. And then in the final chapter of the course, we will deploy a comparable configuration in a real cloud environment. And also, I will show you how to use the latency-optimized geo-partitioning pattern so that we can achieve low latency reads and writes for the users regardless of their location. Okay, so let's not waste a minute and start with the following pattern by deploying our database instance on our local laptop across multiple regions. And the first step, I want to recreate my cluster from scratch, which means that let's tap all of these cluster nodes and I will remove all of them. Excellent. Also, I will recreate the directory that is used as the volume. The next step, let's start the first node. This is how the command for the first node looks like. At the beginning, it's exactly the same as it used to be. We are starting the YugabyteDB node 1 container on the Yugabyte Plus network. However, what has changed this time is we have added these 2 parameters. I'm telling that this node will belong to the following cloud location. It will be running in GCP, Google Cloud Platform. It will be located in the United States East 1 region, and more specifically, it will be deployed in the United States East 1A zone. And you can provide whatever you like in this parameter. I'm providing this value because I'm planning to deploy my production-grade database cluster in GCP in the same cloud location. That's why right now it's reasonable for me during the development. I will reproduce this multi-region cluster on my local laptop. And the second parameter is fault tolerance. I'm telling that my cluster is going to be configured to tolerate region-level outages. Okay. The first node has started. Let's go to the node UI and check it. So that's from the previous chapter where we have stopped the first node in the beginning. But now we need to refresh it. The first node UI listens on this port number. And we have this node. And here is in the region and zones tab, you can see that the node is deployed in United States East 1. Let's move forward and deploy the remaining nodes. So that's the command for the second node. The second node joins the first one. This node also will be deployed in GCP, but in a different region. It will be deployed in the United States Central 1. And Central 1A is going to be the zone. Excellent. And let's deploy the final third node. The command for the third node looks as follows: the name of the container. It also joins the cluster by connecting to YugabyteDB node number 1. The fault tolerance parameter remains the same. It's equal for all of the nodes. However, the cloud location, it's also Google Cloud Platform, but this node will be located in the United States West 2 region. Also, when you're using YugabyteDB to provision your cluster manually, you need to execute a few additional commands. For instance, this one command connects to YugabyteDB node 1, and it uses the YugabyteDB tool to configure the data placement. You do this once you edit all the nodes to your cluster, because right now I have 3 nodes in the cluster. My cluster topology is final, at least for now, and I want to execute this command. And the final configuration step, but that is totally optional, is the definition of the preferred region. Why do I do it this time? Because I'm planning to deploy my distributed PostgreSQL cluster across the United States, from the United States West Coast to the United States East Coast. And I want to minimize the cross-region traffic. I can do this by defining the United States East region as the preferred region, meaning that the nodes that are deployed in this region will be the raft leaders for all of your data, and the nodes from this region will be handling all the application read and write requests by default. It also means that you will be able to connect and serve reads from the other locations such as United States Central or West by using other design patterns such as the follower reads. But this is one of the configurations that I want to test this time. If this region becomes unavailable For instance, because there is some region level outage, then the United States Central one location will become the next preferred region because its priority is set to 2. This is how it works from the high availability standpoint. Done. Cool. Now, let's go back to our UI, and I'm refreshing the tab. Now, you can see that we have this 3-node cluster and every node is deployed in one of the cloud regions. However, before we restart our movie recommendation service and get it connected to this multi-region cluster, I want to demonstrate another design pattern. And that second design pattern, if you remember, is latency-optimized geo-partitioning. As long as I already have that multi-region distributed database cluster, I want to select a table in my application that can be geo-partitioned. Let's say I live in San Francisco, and all my data can be stored in the United States West Coast, not in the East Coast. If I live in New York, I want my data to be stored in the United States East region, not in the West region or any other location. And by pinning user data to the locations where they live, I will be able to achieve low latency reads and writes across distant locations. How about we go ahead and select one of the tables for this geo-partition pattern. Going to the application source code, and in the backend resources, we have these database migration files. For instance, we have this movie table, but this movie table is not specific to any user. There is no way to make it geo-partitioned. That's why the table is going to be just distributed across all of the regions. However, we have this user library table, and this looks like a perfect fit for us. And ideally, we need to store the user-specific information about those movies close to the user. So how about we go ahead and make this table geo-partitioned? What do we need to do? I don't want to change this migration file. I want to leave it as is. Instead, I will create a new file that will be picked by Flyway. Next, in this file, I will define several table spaces. If you're familiar with Postgres, the table spaces allow you to pin your user tables and other database objects to specific locations, such as disk drives. And we are going to benefit from this feature of Postgres for our distributed deployment. But in our case, we are going to create table spaces for specific cloud locations. For instance, this is the table space for the United States East region, and then I'm creating similar table spaces but for the United States Central location. That's their placement blocks, United States Central and Central 1A zone, and the same is true for the table space in the United States West. Next, I want to recreate the user library table. First, I need to drop it. Then, once I create this table, I will ask to partition this table by the user location. And partitioning is also one of the features of Postgres that is supported by YugabyteDB as well. And finally, I am defining these partitions. For instance, one of the partitions is going to be user library USA East. It's the partition of the user library table. I'm defining the columns, and I'm setting the primary key. It's a combination of the user ID, movie ID, user location. And then I'm telling that if the user location is set to New York City or Boston, then please store the user data in the following United States East partition. And this United States East partition is mapped to the United States East table space, okay, that we defined here. And this table space will be deployed on the database nodes from the United States East. So basically, this is how the data will be stored in a specific region on a specific database node. You're just configuring this once, and then the database will do the job for you. And similarly, I defined comparable partitions for the United States Central. That's for the users who live in Chicago or Kansas City. And then if you live in San Francisco or Los Angeles, then your data is going to be stored in the United States West partition that belongs to the United States West table space. Makes total sense. That's it. And now we are good to go and we are ready to restart our application. Let me stop it. And when I'm doing the Docker Compose up, this time I need to rebuild the image, at least for the backend, because I have added this new file and the file is packaged with the image. So it will take probably a minute to recreate the image from scratch. Excellent, the image has been recreated, and now we are starting the backend, and now we are applying the new migration from scratch. That's our latest migration file, where we have created our geo-partitioned tables. The application is up and running. Let's go ahead and check it. We are going to the application UI. As always, need to sign in back. And you know what, my friend, I am in a mood to watch the following movie a long time ago in a galaxy far away. Let's see if the application knows. Certainly, our application managed to find the list of proper recommendations. It's all about Star Wars. Now, let's say that I want to watch the last movie, The Empire Strikes Back. I'm adding it to the library and it appears here. Also, this movie internally in the database is stored in the user library table that we made a geo-partitioned one. So let's see how the data is accessed and stored internally. First, I want to copy the name of this user, and the user lives in New York City, which means that the data of the user needs to be stored on the database nodes from the United States East Coast. Connecting to the database. This is the list of my tables. You can see that partitions in Postgres and YugabyteDB normal tables, they just basically belong to the primary table, user library. If you want to see more details, you can always use this command, a list of partitions that belong to this primary table. Next, I want to find an ID of John Doe. It's stored in the user account table. We know the name of the user. And the ID is as follows. I will copy it. And next, I want to query the user library directly. I want to see all of those movies that are on the watch list of John Doe, where user ID is equal to this one. So what can we say? Yeah, we have one movie on the list. What if we take a look at the execution plan? Explain, analyze. You can see this is what's happening. Even though I'm querying the data of the John Doe, Postgres and YugabyteDB, they send requests to all of the partitions, the United States West, Central, and East location. And this is okay when you don't know the location of the user, but ideally you want to minimize the traffic. If you know that the user lives in the United States East Coast, then what you need to do is to provide the user location value. And this is exactly what the application does internally, because the application is already optimized. New York. And once you provided the location, New York, and John Doe lives in New York, you can see that Postgres and YugabyteDB internally, they query only the United States East partition. Don't need to broadcast this request to all of the other locations. And now, if you remove this explain analyze from here, you will see the same data. Yep, excellent. Also, let's go back to the application and add another movie to the list, the second one. If you query the table right now, you can see that we have two movies that are on the watch list for John. Also, you can request and query every partition directly. It's all possible. User library, USA East. And also, if you want to make sure that this data is stored only in the United States East Coast and not replicated to any other locations, which can be an excellent option for those who need to care of data residency requirements, you can easily validate this. You can query the United States Central partition directly, like this one, United States Central. It's empty, no any data. And you can do the same for the West, nothing. But if you query the East partition directly, you will find this data that belongs to Joe. Excellent, right? And one last check, my friend, before we finish this chapter of the course. I want to go to the application and I want to sign in using a different user account. The email is user2@gmail.com. And this is Emily Smith, who lives in San Francisco, which means that her movies catalog has to be stored in the United States West. Let's go here and query the West partition directly. I want to make sure that it's empty. And let's suppose that Emily is also in the mood to watch some Star Wars movie. Making the search, and she wants to start with her first episode. She adds it to the library. It's here. If we go back to the database connection, I'm confirming that this movie is stored in the United States, the West, because Emily lives in San Francisco, and San Francisco belongs to the United States West Coast. And just in case, I want to make sure that this data is not replicated to the central location or to the east location of the country. Nice, congratulations, we have successfully completed chapter 4 of the course, where you have learned how to use several design patterns for global applications that have to work across distant locations. Specifically, you learned to configure multi-region database clusters, then you learned how to define preferred regions, and finally how to create geo-partition tables. And now we're ready for the final chapter of the course, where we will take our distributed database deployment and make it fully cloud native. Alright, my friend, in this final chapter of the course, you will learn how to deploy your database in the real cloud environment and use it as a fully managed service. Suppose that you are done with the early development cycles and you're planning to deploy your application to production or pre-production environment, and you are planning to deploy everything in the cloud. So you will find a way how to deploy your application instances, but when it comes to the distributed PostgreSQL deployments, the best approach is to use YugabyteDB managed, okay? And what you can see on the screen, I have already connected to the YugabyteDB managed using my personal account. Let's configure and deploy our fully managed cluster. The process is going to be straightforward. You have two options. You can deploy a cluster in a sandbox environment, and that's going to be just one single node for your experiments, or you can move forward with a dedicated cluster. This is exactly what I need because I have already selected a desired cluster configuration. We have tested that multi-region cluster on our own local laptops, and now I want this cluster to be available in the real cloud environment. In our course, we used GCP. That's why let's use Google Cloud here. Next, you can deploy your cluster in a single region or multi-region. We used the multi-region approach locally, so that's why let's pick this option. Then when it comes to the data distribution, you have two options. You can replicate your data across all of the provided regions, or you can partition by region. And the partition by region approach works perfectly well if all your tables are geo-partitioned. But in my case, only the user table is geo-partitioned. The other tables are standard tables. That's why I'm selecting the replicate across regions approach. The other settings I will leave untouched, but then I want to provide the names of the regions, and I want them to be the same as those that we have selected and tested locally. United States East 1, Central 1, and West 2. And this is the connection to my locally running YugabyteDB cluster. Let's pick them here. United States East 1, and we're interested in the East 1 in the United States. It's going to be preferred region. Then we Central 1 in Iowa, United States, and the last one is West 2 in Los Angeles. Then, moving forward, on this screen you can add a list of IP addresses that will have access to your cluster, or you can configure VPC connections. I will create a new list. I will add my current IP address, and this is my personal laptop. Enable public access. That's what I want to do. Next, I don't need this. And as for the database credentials, you can always define your own credentials for the database, or you can use the ones that are pre-configured by YugabyteDB managed. But don't forget to download this file with credentials. I'm saving this. Let's go ahead and create our cluster. It started, and it will take a few minutes to get our cluster running and ready for our application. Let's take a break. And our multi-region cluster is ready. We have 3 nodes, and those nodes are spanning across the United States West, East, and Central location. Now I'm ready to get my application connected to this multi-region cluster. However, before I restart my app, I need to make sure that the zones that were selected by YugabyteDB managed correspond to the zones that I defined in my table spaces configuration. Zone names end with B for every region. And if I'm not mistaken, in my geo-partition table configuration, it's a little bit different. The region names remain the same because I have selected them, but I need to adjust the names of my zones. Done. That's it. Next, let's go to the settings tab, where we can find connection endpoints. I'm located in the United States East Coast, and this is also the preferred region. I want to connect to this one directly, that's the IP address. Then go to your Docker Compose file. I will be using the same YugabyteDB smart driver. That's my endpoint. I no longer need load balance, at least for now, because this endpoint already acts as a load balancer for me. However, SSL mode has to be required. And finally, remember that during the configuration you download that file with credentials. So my username is admin, and the password looks as follows. You will have a different password. And by the way, even though YugabyteDB Manage configures these passwords, it doesn't store them internally. Only you have access to this password. And that's why it's important to download the file with credentials during the configuration step. Cool. I'm ready to restart my application, and as long as I updated this file with the database migrations, I adjusted the names of the zones, I need to rebuild the image. Let's stop our application. It was connected to my locally running cluster, and now I restarted and I'm asking to rebuild the image. The new image is ready and the containers are being deployed. I can see that my application successfully connected to my fully managed YugabyteDB cluster, and right now it's applying the database migration files. All the migration files were applied without any issues, including my last file where we configured this geo-partition table and table spaces. With that, the application is up and running. Let's jump back to the managed interface. And if you go to the tables tab, you will find all these tables, and also you will find partitions that we defined in our configuration file. And with that, I can't wait to test my application. Jumping back to the application UI, certainly we need to reconnect, because right now the application is connected to my cloud-native database deployment, and I'm in a mood to watch some movies about spies and secret agents. So let's be just specific, secret agent. Excellent. I've got a few options, and right now the application connects to my multi-region cluster in the cloud and performs the search. Wonderful. Congratulations. You have successfully completed chapter number 5 of the course, where you learned how to deploy your distributed PostgreSQL clusters in a cloud-native way. Alright, my friend, the course is over. Job done. Thank you for watching the course till the end. I hope that you liked and found it useful. As a reminder, throughout the course you learn the essential capabilities of distributed PostgreSQL deployments that let you design and build scalable and fault-tolerant applications. Now, you can pick a topic and dive deeper and learn more about those types of deployments and applications. In the meantime, in the description to this video, you will find a link to a step-by-step tutorial that will let you reproduce all the steps on your own laptop. Keep mastering databases and stay tuned. Bye bye now.